Akleek Island, approximately 75 miles wide. It lies 700 nautical miles from the North Pole and is uninhabited except for occasional polar bears. At 6 a.m. on the 5th of September, wind on the island was from the southwest at 3 knots. Temperature was 26 degrees Fahrenheit, and barometric pressure was 29.4 inches of mercury. Broadcasts of weather are automatically made from Axel Heiberg every 3 hours, 24 hours a day. It is a free contribution to the world community. For across the wastes of the Arctic, the weather begins that eventually sweeps down into the backyard of half the world. If we are ever to learn about the makeup of the storms in the Northern Hemisphere, we must learn it here. But weather information on the Arctic is scattered and fragmentary. A year-round automatic weather station on Axel Heiberg will fill in some of the gaps, will chart the wilderness of Arctic weather. The broadcast originates with a small weather station installed on the island on the 17th of August, 1961. Power to run the recording and transmitting equipment comes from atomic energy. The specific power source is the radioisotope strontium-90, which gives the generator a design life of 10 years. But strontium-90 seems at first glance a very unlikely isotope for any such peaceful use in society. It has a half-life of approximately 28 years and emits intense ionizing radiation. Even though the radiation decreases with time, shielding must be provided for decades. Strontium-90 is mainly produced as a byproduct of reactor operations. Many radioisotopes are produced in this way that we cannot fully use at present, but which must be safely controlled. By 1961, large quantities of strontium-90 and other radioisotopes were being handled as waste from reactor operations. 4 major facilities of the Atomic Energy Commission have acquired extensive knowledge of waste disposal and storage. The Hanford Atomics Products Operation in Washington State, the Idaho Chemical Processing Plant, the Savannah River Plant in South Carolina, and the Oak Ridge National Laboratory in Tennessee. Generally, 3 major methods of reactor waste handling are used at these facilities: radiochemical processing, underground storage, and soil retention. Therefore, storage differs at various sites. Methods of removing the heat generated during decay of the radioisotopes also differ. For example, radiochemical processing is conducted in the Fission Product Development Laboratory at Oak Ridge. Valuable isotopes for use in medicine are recovered in this way. Industry uses isotopes for many applications, including gauging and radiography. In agriculture, animal metabolism studies with tracer quantities of isotopes have increased milk production. Another technique to reduce storage facilities for very low-level waste is that of soil retention. After acidity adjustment and concentration meet AEC health and safety requirements, low-level wastes are discharged into the soil of controlled areas. But high-level radiation waste must be safely stored in large underground tanks. They are generally metal tanks holding up to 1 million gallons of liquid waste. Cost estimates on this method range from 30 cents to $2 per gallon, but it is still the safest and cheapest way to contain high-level wastes. But storage is an unproductive end for energy contained in radioactive waste. Therefore, AEC's Division of Isotopes Development awarded a contract in 1958 to Martin to study the use of strontium-90 as a heat source for small-scale generation of electricity. The job was to convert unproductive quantities of strontium-90 into a useful compound for peaceful applications. The development of a remote automatic weather station was to receive particular attention. Strontium titanate was chosen from many compounds studied because of its extreme insolubility in fresh and seawater. In freshwater tests, strontium titanate was undetectable, while only 0.3% of strontium titanate dissolved in natural salt water after 2,400 hours testing at 150 degrees Fahrenheit. Compound studies also demonstrated that strontium titanate has high strontium density, that it is stable at temperatures far above operating conditions, and it is resistant to thermal stress. Strontium-90 for the weather station was shipped from Hanford Atomic Products operation to Oak Ridge in specially designed casks. The isotope was processed in the Fission Product Development Laboratory. The first major step is a wet chemistry process. Strontium is finally precipitated as the carbonate in the presence of titanium dioxide. The precipitate must be filtered and dried. Wet chemistry is followed by calcination. The compound is withdrawn from the filter and placed in a furnace to decompose the carbonate. This will give us a powder to compact into pellets. Sintering converts the discs of strontium titanate into a ceramic form. Only 1 pound of fuel is required for the 5-watt generator used in the Arctic. Once loaded, the fuel capsule or container must be welded tight. Some 17,500 curies of strontium titanate have been placed in the capsule. The capsule, in turn, will be loaded in a thermoelectric generator. A thermoelectric generator is a device for the direct conversion of heat into electricity. It makes use of a principle discovered by Seebeck. He showed that a continuous electric current would be produced when a thermocouple consisting of 2 dissimilar metals connected in a closed circuit has its junctions maintained at different temperatures. Thermocouples had previously been used for temperature measurement, but it was the development of thermocouples fabricated from semiconductor materials such as lead telluride that made practical the production of electrical power by this principle. The weather station generator uses 60 such thermocouples made from lead telluride. The heat produced by the decay of strontium-90 maintains the hot junction temperature. Cylindrical in shape, the generator is 20 inches high and 18 inches in diameter. The generator weighs 55 pounds and is shielded by 4.4 inches of lead weighing 1,600 pounds. The fuel is contained in a single capsule made of Hastelloy C. It has a design life of 500 years. The capsule is housed in a cylindrical sleeve, also made of Hastelloy C, which serves as the heat junction. The thermocouples and a heat sink complete the generator design. The generator powers all of the automatic equipment of the weather station. The weather station, apart from the generator, consists of the data processing equipment, the measuring systems, timers, chronometer, and the 2 single sideband transmitters. A 24-volt battery is constantly being recharged by the generator. The station transmits 4 basic weather conditions: temperature, barometric pressure, wind direction, and average wind speed every 3 hours. On receipt of a start signal from a master timer, the data processing equipment reads and stores data from all instruments. It generates the station call letters, VA, converts the data to a binary code, and sequences it to the transmitters. Broadcasts can be picked up at a receiving station several hundred miles distant. Decoded, the weather information can be relayed to major meteorological centers on the American continent. Acceptance tests on the generator and station equipment were run from May through 10 July '61. In the laboratory, an electrical heater powered the generator during initial tests for 35 days. The loaded generator was then received from Oak Ridge National Laboratory, and the complete weather station was erected at the contractor's facility for a full-scale checkout. The generator went underground on the 1st of June and powered the station for 40 days. It broadcast successfully during this time to a receiving station in Washington. The first strontium-90 weather station was ready for active duty in the Arctic. Ahead of it lay a journey of almost 4,000 miles, made possible by joint Canadian-United States teamwork. The station was first trucked from Baltimore to Montreal, and on the 24th of July, it was loaded on board the Canadian icebreaker, the John A. Macdonald. As the Macdonald made its way north, the Royal Canadian Air Force flew an international weather team into the last outpost of northern Canada, Resolute. From here north, things get a little primitive. At Resolute, the first job was started. Antennas were erected for future transmissions. As they went up, the Macdonald swung into the harbor with the weather station and the equipment to complete the receiving station. Men and supplies were loaded on the 12th of August. By noon the next day, the small task force was underway. The Macdonald set its course from Resolute around Devon Island, through the narrow passage of Hell's Gate, bound for Graham Island, Northwest Territory. But, as we shall see, problems developed at Graham, and the Macdonald was forced to turn further north. It landed the task force at Sherwood Head on the southern tip of Axel Heiberg Island. As the Macdonald skirted Devon Island on the second day, it began running into floating ice. A helicopter flew out regularly to scout a passage ahead. Glaciers were spotted on the north coast of Devon the second day out. Ice thickened. At Hell's Gate, it was running solid at depths of 4 to 6 feet. As the ship approached Graham Island, the ice closed in. It was now 8 feet deep. After fruitless searching, the helicopter returned to the ship. There would be no passage to Graham Island on this trip. A decision was made to proceed to an alternate site at Axel Heiberg, which had been selected earlier for just such an emergency. This time, the weather and luck held. A clear passage was found into the harbor, and as the Macdonald made its way into the final stages of the journey, the two helicopters landed the advance party to begin survey of the site. It was 6 p.m., 15 August. Luck seemed to smile on the party. They found the permafrost level at 4.5 feet. Large-scale blasting was unnecessary. Captain Cuthbert, skipper of the Macdonald, now ordered his entire crew to pitch into the job. No one had asked for their help, no one had expected it. But it meant that 30 Canadian sailors and 11 regular members of the task force, 41 strong backs in all, began unloading with a vengeance. A bulldozer served as the all-purpose vehicle on the ground, hauling supplies from shore to site. The first of the 3 antenna masts was up within 24 hours. The mechanics of the job continued to go smoothly, and the telemetry package was first checked out using 4 6-volt lead-acid batteries. Within 30 hours, ship-to-shore communications confirmed contact with Resolute. We were ready for isotope power. The strontium generator was connected, the chronometer was synchronized, and the barometer set. The assembled station was lowered into its housing in the ground, and soil bulldozed around it. Only the top and snorkel tube protecting the antenna wiring remained above ground. The generator will maintain an average temperature of 70 degrees within the station, protecting the electronic components from Arctic cold. The station was now on its own, with a warning to unlikely Arctic visitors. The last of the installation party returned to the ship. There they awaited word from the receiving station at Resolute to tell them whether or not the job was done. The wait was short. Resolute received the first broadcast. Decoded, it read, wind at 2 knots from the northeast, temperature 38 degrees Fahrenheit, barometric pressure 29.92 inches. Captain Cuthbert came out of the radio shack with the return wire just 48 hours after he had landed the advance party on the island. And the first nuclear weather station in the Arctic, or anywhere else for that matter, was in business. There was plenty of credit to go around before everyone decided to get some sleep. The Arctic station is not the end of the journey, or the end of peaceful use of strontium-90. Vast stretches of the sea, some 3/4 of the Earth's surface, offer an ideal environment for remote automatic devices powered by radioisotopes. SNAP 7A generators for light buoys and SNAP 7B units for fixed navigational beacons powered by strontium titanate are well advanced into hardware. These units only scratch the surface, but they indicate the wide breadth of potential applications. Buoys with radioisotopic power sources will increase their service life many times. Older maintenance practices will be radically simplified. For example, as many as 72 wet cell batteries are used in some buoys. Just the recharging and handling of these buoys demand costly maintenance facilities. They are brought in from the sea and recharged every 6 months. If we substitute isotopic-powered systems for batteries, we will eliminate this type of maintenance problem. And of course, additional remote weather stations are a logical development. This is a SNAP 7C generator. It will power a companion weather station at the other end of the Earth from Axel Heiberg, going into operation at Little America Station number 5 near the South Pole late in 1961. Indeed, we need only a short look into the future to see that isotope power generators will use increasingly significant amounts of strontium-90. The AEC is turning its attention to other fission products, such as cesium-137 and cerium-144. As increasing quantities are put to use, we will enter a new era, an era where radioisotope waste will be transformed to wealth. Strontium-90 becomes a servant of the nuclear age.
This is National Educational Television.